If you want to determine if two substituents on a cyclohexane ring are cis or tran, you need to see whether they're on the same side of the ring or on opposite sides of the ring. So if we plane a representation of a cyclohexane, then if you have two things that are both shown with a wedge, so for example this CH3 here and this bromine here, because they're both shown with a wedge, these are cis. They're both coming towards you out of the page. They're both towards the top of the ring, if we call the top of the ring outside of the page. So this would be an example of cis. If instead one was a wedge, so let's put our CH3 as a wedge, and the Br was a dash, then one of them's coming towards us out of the page, that's the CH3, while the Br is going into the page. So they're on opposite sides of the ring, so we call this trans. If we wanted to put these into chair conformations, then over on this chair conformation on the right here for the first one, we just need to pick any carbon as being our number one, which I'm going to arbitrarily put as the one with the CH3 on it. So let's say that I picked this carbon right here to be that number one carbon. Well, CH3 goes up. Okay, well the two possible orientations of substituents on this ring are straight up in the axial position or down in the equatorial position. I'm going to call this up here the top of the ring. And so if I want the CH3 coming towards me, towards the top of the ring, I need to put the CH3 up in this axial position. The other substituent off of this carbon is the hydrogen. Now if we want to go over to the number 2, that will be right here. And so now off of this one, the two possible orientations are straight down in the axial position or slightly up in the equatorial position. We want the Br to be going up. Out of these two possible positions, the one that's closer to the top of the ring is this equatorial one, the Br. So there's the H. So this is what this cis molecule looks like in its chair conformation. So what you do to figure out if you were given just the chair conformation is you'd look at one carbon and you'd look at the two substituents on it, the H and the Br, and you'd say, okay, the Br is closer to the top of the ring. You'd look at the other carbon and you'd say, okay, there's an H and a CH3, and the CH3 is closer to the top of the ring. Both substituents are closer to the top of the ring, and so this is cis. If we wanted to draw the other chair conformation, then we could just pick any carbon which is going to put the CH3 group, now instead of the axial position, we want to put in the equatorial position, and that will represent the chair flip of this molecule. One way that we could do that is pick this as carbon number 1. The reason I know I can do that is because it's a down point, the substituent position that's going to be closer to the top of the ring, so still up, is going to be equatorial. So I can put the CH3 there. Now this carbon here will be number 2, and the possible positions are straight up or slightly to the right here, and the Br needs to be on top, closer to the top of the ring, so there it is there, and here is the hydrogen. So this is the other chair conformation. You'll notice that the Br, which was equatorial, is now axial, so both substituents have switched their relative orientations, but they're still, in relation to the carbon they're bonded to, they're still both the substituents that are closer to the top of the ring. It's still cis, and they're still both closer to the top of the ring, even though they've switched their axial versus equatorial positions. Now, if we wanted to figure out which of these was more stable, then the more stable one is the one that puts this Br in the axial position versus putting the CH3 in the axial position, because the CBr bond, so this bond right here, is longer than the CH3 bond, and that puts it out of the way of these shorter CH bonds. So this Br has very little interaction with these H's, whereas the CH3 over here has a lot of steric interaction with these axial hydrogens. So this over here on the right is more stable because the CBr bond is longer, and it gets it out of the way of those axial hydrogens, so there's not as much steric interaction. Now for the bottom, for what trans looks like on cyclohexane. So let's pick this different carbon now as our number 1. So let's say we put it